perfect. So we're going to let u equal this term underlined in yellow, and then du, Lou, you just gave that to me, would be minus sine of 13t times the derivative of the inside, which is 13. Now, I'm going to multiply both sides of this equation by dt to get du equals negative 13 sine of 13t dt. So I'm lining myself up for the u substitution that I want to make. And let me look back up at my integrand. That's what I've got in my integrand. And that's almost what I've got here. But what I got to do is I got to get rid of that minus 1 or minus 13 here. So I can do that by multiplying both sides by the reciprocal. So let's do that. So it's going to be negative 1 over 13 du equals sine of 13t. What's wrong with my pen this morning? Sine of 13t dt. And that's perfect because now I've got a nice direct substitution for what's in my integrand. This part right here, let's see, how come it's not here? This part right here is exactly what I have in my integrand. So I can replace that with negative 1/13 du, and the rest of it is going to be e to the u. So let's do that. So the integral of e to the u, I'm not sure what's wrong with my pen here, times negative 1/13 du. Now that negative 1/13 can come out in front times the integral of e to the u du. Okay. Then what? Then what's going to happen with that? Well, we know the integral of that, right? What's the integral of e to the u? You know what? I lost a negative in here. There we go. All right, someone make me look good. What's the integral of negative, or excuse me, of e to the u?
E to the u.
E to the u. Anything else? This is actually an important part, and I think that's why the person asking this question got this one wrong. It's negative e to the u plus a constant. And they asked you that your constant be in capital C.
Ah.
So if you're getting something wrong, you're like, oh, get it. It could be that constant. Now, we're not done, though, right? Because we're trying to find the antiderivative of something in t, and right now we've got something in u. So let me finish this off. U was cosine of 13t plus a constant. So cool. That does it for this one. And the only thing I can see wrong with this person's answer is that they forgot the C. So now, I hope that doesn't happen to you, because with WebAssign, it's more of an all or nothing thing. And I don't want to see you get nothing if all you forgot was the constant. So, okay, how's that one looking? Pretty good?
Yeah.
Okay. Let's take a look at another one. And that would be this one here. Sine of t times the square root of 1 plus cosine of t. Now, there's not really a formula for, what you should always let u equal when you're doing your u substitutions. And in fact, you don't want to do a u substitution unless you really have to. Okay, if there's other ways to do it, hey, great, do it. But in this particular case, let's see, did we get another participant? Yes, we did. There we go. In this particular case, what draws my attention is that, again, you have part of the integral that's the derivative of another part. So this part here is a derivative of this part here. Can you see that? If you let u, I don't want to do it there. Oh, there we go. If you let u equal, come on, what's wrong with this? U equals 1 plus cosine of t. What's du going to equal? Well, I'll kind of cut to the chase a little bit. Du is going to be sine of t. It's really du dt equals sine of t, but if I multiply both sides by dt, I get this. Du equals sine of t dt. And that's perfect because sine of t dt is actually what I've got here in my integrand. So let me erase that a little bit. That's my u. But what I have underlined in blue, that's my du term. And that's perfect because that's all right here. So I can replace this with the integral of, let's see. Well, let's see.
Jeff, should it be minus sine t dt?
You're right. Thank you. So that means I need to move the minus sign to the other side by multiplying by -1 and get du minus du equals sine of t dt. Okay, so let's continue then. This is 1 plus cosine of t sine of t dt. And that's what I wanted because this thing now matches. So it doesn't hurt to necessarily take an extra step and write down what you've got so you can see how things are gonna substitute and shake out. So we've got our u, oops, got our u, which is right here. And here. So let's make our u substitution then. And that's going to be the integral of the square root of u times minus du. And from there, we want to clean things up a little bit before we integrate. Let's take that constant of a -1 out in front. So negative of, how am I going to rewrite the square root of u? Any suggestions?
U to the 1/2.
Good, u to the 1/2. So u to the 1/2, and the antiderivative, well, we're going to have -1 times u to the 3/2 divided by 3/2. Let's not forget our constant. And then we'll come over here, finish that up. That's going to be -2/3 of u to the 3/2 plus our constant. And finally, -2/3 of 1 plus a constant, or 1 plus cosine of t to the 2/3 plus c, plus capital C, right?
To the 3/2, right?
3/2, yeah, my bad, 3/2. That is one thing I really like about using OneNote here is I can erase that stuff pretty easily. Just not really crazy about the quality of my printing sometimes. But I hope it's legible enough. Okay. How are we looking on that one? Ooh, pretty good. Yes?
Yeah.
Okay. Let me just check in on crowd here. Mute all. Other reviews, haven't heard from you today. I mean, feel free to ask questions or make comments, whatever you got going. This is your time. So get the help that you need. Let's move on to another one. Square root of, actually, is that a cube root?
I think so, yeah.
Yeah, it's a cube root. Cube root. All right. So let's go back and do this one. Cube root of 1 plus 7x dx. Now the problem is that 1 plus 7x term, let's see if I'm, let's just delete that. So I think it was 0 to 1 of the cube root of 1 plus 7x dx. Now, if it was just x to the 1/3 power or something like that, we'd be able to find an antiderivative with no problem. But the radicand, that little part right underneath the radical, that's going to be kind of a pain. So we can get around that with a U-substitution. Now, the nice thing about this example is that it's going to involve switching the limits, or at least the way I do it, it switches the limits. I'm going to let U equal 1 plus 7x. du by dx would be 7. Let's see. There we go. And one more. 7. So du equals 7 dx. Now looking at what I have in the integrand, I've just got a dx. So I'll divide both sides by 7 to get rid of that 7 from the right-hand side and get 1/7 du equals dx. And then what? Then let's also change our limits of integration here, because this is a definite integral. It's no longer just a regular indefinite integral, not just looking for an antiderivative. So I'm going to plug in two numbers. I'm going to plug in u of 0 and u of 1. So if I plug in a 0 into my expression up here, what am I going to get for u? What's my new limit going to be?
The lower limit?
Yeah, u of 0.
It should be 1.
Thank you, 1. And u of 1 would be?
8.
8. Good. All right, so let's do all our changes here. We've got a substitution for dx. And yeah, I think we're ready to finish this one up. So it's going to be the integral from 1 to 8 of the cube root of u times 1/7 du. Oh, God, that's horrible. So 1/7 du. Now that 1/7 can come out in front. 1 to 8. What am I going to do with the cube root of u? U to what power?
1/3.
Good, U to the 1/3 power. So now you're at a point where you can find an antiderivative. We'll add 1 to the exponent. So it's going to be 1/7 times the antiderivative, which is going to be U to the 4/3 divided by 4/3. Now, dividing by 4/3 is like multiplying by what?
3/4.
3/4. So that's going to be 3/28 times the function U to the 4/3 between 1 and 8. So I like leaving that constant out in front so I don't have to keep on writing it. So it's going to be 8 to the 4/3 minus 1 to the 4/3. So 8 to the 4/3 is going to be 16. Minus 1 is 15. So what's inside here is 15 times 3/28 is going to give me 45/28. Whew. Okay. A lot going on there. But the important thing to see here is the change of variables. We went from our function in U to our function, or excuse me, our function in X to our function in U, and doing that change in variables is key. And that was right here. Nice. That one worked out good. How are we looking on these? So far, so good?
So far, so good.
So the 1/7, where it says 1/7, like 1/8, and then U to the 1/3, is that times du?
1/7 times du, yeah. This part right here?
Oh, okay. Okay, perfect.
Yeah. And so when we did our substitution, that was right here as well.
Yeah, you substituted that in for the dx. That makes sense, though.
Perfect. Yeah. And that's, I mean, look, there's other ways to do it. I'm not saying mine's right, but some people do it differently, and that's fine. I just think this is the path of least resistance. Makes a lot of sense, and it's easy to follow along. All right, there's 2 more problems that we've got here that were emailed to me ahead of time. So let me do those. And let's see. Yeah, the first one here that I want to do, oh my, that's this one right here. This one's a good example because it shows you kind of a little bit of a tricky U-substitution. So let's work on that one. Boy, didn't scan in very well. So tell you what, let's do some different technology here to do this one. So it's the integral of e to the 49th, e to the 81st times dx over the square root, or x times the square root of ln of x, like that. So time for some new technology. This is cool. I've been waiting for this for so long. Okay. Zoom in a little bit. Now, the trick on this one is that we want to choose ln of x for the substitution. And the reason for that is because our du term is actually already there. And let's take a look at it. So if I let u equal ln of x, let's take a look at du by dx. What's that going to equal?
1 over x.
Good, 1 over x. And then du, multiply both sides by dx, is going to be dx over x, or 1 over x times dx. And the good news is that we've got both of those terms here already. So you guys have been missing this orange pen, I can tell. All right, so that is right there. And that's really cool. So with that, I'll have 1 over the square root of u, and then I got to change my limits of integration. So let's see what's going to happen there. If I plug in this limit, the upper limit, u to the 81st, that's going to be the ln of, I said u to the 81st, didn't mean that. ln of e to the 81st. Can someone tell me what that's going to equal?
81.
Yeah. 81 and 49 respectively. So, okay, nice. Let's keep going. We've got everything we need to make our U-substitution. Our new limits are going to be between 49 and 81. And I'm going to have this term is my du term, right? Right here. Let me go back to a familiar stick with you guys. All right, all the multiple colors. So that's my du term. I'm still going to have du over the square root of u. Wow, that looks a lot simpler. How am I going to work with this, though? How should I rewrite this in order to move on?
U to the negative 1/2.
Perfect. U to the negative 1/2 du. Then I'll end up with, let's see, the square root. Well, let's find the antiderivative. 49 to 81. It's going to be u to the 1/2 divided by 1/2, or better yet, 81 divided by 1/2 is like multiplying by 2, so twice the function square root of u between 81 and 49. So twice the square root of 81 minus the square root of 49 is going to be 2 times 2. Whoops, ran off the screen a little bit. So 4. Yay. Wow. Not bad. I strongly suggest that when you're doing these things that you that you do your U substitutions like I do. I mean, there's other ways, but if you're not going to do the change of limits, then technically up here you should have like an A and a B, because the limits in the integral U wouldn't be the e to the 49th and e to the 81st that you started out with. So you'd have to write an A or B, or sometimes I write question mark and question mark, and then just plug all the X's back in when you're all done. But that, it just feels like so much more work to do that. I don't like it. But whatever works for you. Whatever works for you. All right. We've got one more of the pre-planned ones, and this one is a good one. If you take me for Calc 2, you'll probably see something just like this. You'll probably see something just like this in this class, because I really like this one. And there's a couple important lessons that you can learn from doing this one. So let's take a look at this problem. I don't particularly know which one it was in the homework, but it's there. And there's a couple important features that you should know about this. So the first thing that I did here in doing this problem is I said, you know what, I'm going to split this up a little bit. Now, how do you split that up? Well, this term here is going to multiply this term here and this term here. In other words, I'm going to distribute that to both terms. And I didn't do a great job with that second one. Let's try it again. There we go. And so that gave me my two integrals, right? It gave me this one over here. Let me maybe do this. So it gave me this one over here, and it gave me this one over here. So do you see what I did? I split it up by distributing this, and then I pulled the two integrals apart. Are we okay with that first step?
Yes.
You know, let me just kind of write in one like intermediate step here. The integral from -2 to 2 of x times the square root of 4 minus x squared boy, I'm not sure why my pen's not cooperating with me today. 4 minus x squared plus 3. God, this is really horrible. This is why I wanted a document camera. 3 times 4 minus x squared, all of that dx. So if you just distribute that term, and I'm sorry that the writing is just so awful, but if you just distribute that term, then we can split up the integral, which is what I did. I split it up into two pieces here and here. So I'm hoping we're okay with that split. And let's look at the first one. And I've called these problems before finding the integral without integrating, because you can if you're clever. And there's a lot of good stuff here. So let me get going with our U-substitution. You can see here that this is the first integral over here is right for a U-substitution, because if I let that be my U, then this little term is going to be part of my du term, the x dx. And you see the x dx down here. Let u equal 4 minus x squared. And this is my U substitution. But there's something funny that happens. If I change my limits of integration, when I put in a 2, 4 minus 2 squared is 0. Okay. When I put in the -2, 4 minus -2 squared is also 0. So I'm ending up with this right here. Can anyone tell me what the value of that integral is?
0.
Better yet, it's 0. Why is it 0?
If you have a variable to an odd power and the bounds are the same, like -2, 2, or -1, 1, and so on, it always equals 0.
Okay.
Because I got this wrong like 5 times, and then I went online to like Khan Academy or one of those things, and they said when you have a variable to an odd power and the bounds are just a positive and negative of the same thing, the integral always equals 0.
Let me give you a little bit more precise feel for that. This is an odd function. It's not just an odd power, it's an odd function. And that's kind of hard to relate to, but let me show you what's going on. Now, even more to the point, as far as this particular one is concerned, take a look at the upper and lower limits. I mean, if you found an antiderivative here, you could. In fact, it would be 2 times, no, it wouldn't be 2 times, it would be 2/3.
2/3 u to the 3/2.
U to the 3/2. But can you see what's coming? I mean, it doesn't matter that I have 0 and 0. What matters is that these two are the same. So when I put those in, if the limits are the same, I'm going to be subtracting something from itself. I'm going to get 0. So that first one, after all this analysis, turns out to be 0. But I promised Matt that I'd show you guys a little bit more on that. And let me come through with that. Up here. Here's the graph of that function. So it's an odd function because when you draw any line through the origin, in fact, I can do that here. Let's see. Come on. Come on. It's not letting me. Are you seeing my Desmos graph?
Yeah.
Yes.
Well, you're going to just use your imagination here a little bit because it's not responding to me here for some reason. But oh, that's a bummer. Any line through the origin is going to intersect the graph at symmetric points. You have a point up here, and a point down there, and guess what's in between? The origin. So that's a symmetric function. Really bummed that this isn't working.
Because if you don't end up with something that's an absolute, basically you have the difference of, what is it? Basically, area under the curve, you have a positive and negative version of the same thing. So that's wow.
That's exactly right. So what happens with these odd functions over symmetric intervals is that this area down here, and I was so clever, I had this done ahead of time. I don't know why it's not working here. Anyways, this area down here and the area up here are the same, but when you integrate, this one's going to have a negative sign, this one's going to have a positive sign. And adding those two together, they're going to add to 0. So the moral is if you ever see an odd function integrated over a symmetric interval like -2 to 2, you're going to get 0.
What the part that determines whether it's an odd function or an even function, because there's an x squared that's inside the square root, and then there's an x outside. Do you add all of the exponents involved?
No, it's not really an adding an exponents thing. I'd probably have to direct you to one of my college algebra videos, but it's an odd function. If it satisfies this. Boy. If f of negative x equals negative f of x. So basically, if you plug in a negative x into your function, and then it feels like that negative that negative sign can factor out. So examples of odd functions would be x tangent, x cubed, x to the 5th, those kind of things would be odd functions. Whereas even functions are a little bit different. There, f of negative x, well, that negative disappears. It's f of x. So there'd be something like cosine or the absolute value or x.
But the x squared that's inside the square root, that'll take care of the negative sign because it's squared, but the extra outside of it, you're going to get the negative back.
So what's happening here is you've got an odd function times an even function, because the odd function's on the outside, that's the x, times the even function on the inside, that's even. You know, it's just like multiplying regular numbers. Odd times even is going to be even. Well, let's see. No, I guess that doesn't work. Odd times even in numbers is going to be even. Yeah, but this one, an odd function times an even function is going to be odd. All right. I guess what should pique your interest is if you ever see a symmetric interval, start looking out. You know, start going, wait a minute, something's going to go on there, and you'd be right. Okay. So the first part is 0. And if you'd seen that originally, you wouldn't have to do any integration at all. You just say, oh, okay, odd function over symmetric interval, 0. So the first part you can do without integrating. How about the second part? So let me factor out the 3 here. What happens when I factor out the 3? I get this. I get this part right into here. Does anyone recognize that function? If I graphed that, what would it look like?
Circle.
Pretty close, the top half of a circle, right? Yeah. But yeah, let's top half of a circle. Now, there are ways you can find an antiderivative that'll work here, but let's look at what we're being asked. We're being asked to integrate this function from -2 to 2. And what's that going to mean? It's just going to mean finding the area of this half circle, right? So do we need to integrate to find that area?
Well, you have the radius
No.
2, and it goes from 0 to pi. So, and then it's a half circle, so you divide the whole thing by 2. So no, you don't really need to.
No, yeah, you don't. So let me clean this up a little bit. Lasso. Let's get rid of, I guess we don't need to do that.
And it's
So
the square root of any function squared, or a square root of anything within a variable squared is always a circle.
I'd say functions like this, r squared minus x squared.
Oh, so as long as the constant inside the square root is also a square, then you've got a circle. So like minus x squared, 16 minus x squared, and so on.
Yep.
Cool, cool.
So when you have, say, y equals that, you're going to have a circle. But the area formula for a circle is pi r squared. Since we're dealing with just half of that, it's going to be 1/2 pi r squared. So let's see if we can't find the area then. So our overall area would be 1/2 times pi times, well, what's the radius that we're dealing with here?
2.
2. So I'll get 4 pi times 1/2 is going to be 2 pi. So all of this down here, excuse me, all of this up here turns into 3 times 2 pi, which is 6 pi. And that's your final answer, because remember from the first part we got 0. So the cool thing about this is that you didn't have to integrate at all. If you're looking at this carefully, you'll see that the first part is going to be 0 because it's an odd function over a symmetric interval. Second part is just 3 times the area of a half circle. So again, you don't actually have to find an antiderivative here. And those are a couple cool lessons for this problem. So thanks for that question, Mel. All right. I've done a lot of talking here, done a lot of problems, but maybe you've got some more. So fire away.
Hey, Jeff.
Hey, yeah.
I emailed you
Yes,
a couple of problems.
I did all the problems. Oh, wait, is this Alonzia?
Yeah.
Oh, okay. I didn't see those. So, yeah, let me, did you email them or did you put them in the chat?
I emailed them because I didn't know if we was gonna have technical difficulties like before, so I just emailed them to you.
Okay. Let me see if I can spot them. Here we go. Open. Okay, let me copy that and paste it in over here. Glad to see an area problem. Uh-oh. Paste. Let me try it one more time. copy, paste. It's not liking that. Why is it not liking that? Copy. Last chance. All right, I'm not sure why it's not copying. But let's approach it from a different point of view. Maybe
You might need to save that bit as an image file, and then when you go back to the last screen you were on, insert the image file. I don't know if it's gonna.
Yeah, it's just not liking it for some reason. Let me see, desktop. All right, so let's see if we can't do it this way. Desktop, calc problem. Man, technology is not cooperating with us today.
Might need to save it as a JPEG.
Oh, there it is. Let's see. Copy. Paste. Okay. Let me see if I can't make that a little bit bigger here. So we got functions of e to the x, x squared minus 1 between -1 and 1. So, okay. Let's draw a typical approximating rectangle. All right. Let's do that. And let me go back over to my camera. Let's see, mute all. This one. Okay. So y equals e to the x, y equals x squared minus 1, x equals -1, x equals 1. So those are my functions. And I want to evaluate, or I want to look at a typical interval or typical approximating rectangle somewhere in here. Now the function e to the x, when you graph it, that's your exponential growth. I talked about that in my video about the COVID virus. And then our other function is this one, y equals x squared minus 1. That's just going to be a parabola. So something like that. At some point, these two are going to cross each other. I'm not sure exactly where it is, but they are going to cross each other. Nonetheless, what we're interested in is the a typical rectangle. So what I like to do, and in fact, if you watch my video on this section, you'll see it, is I like to start out with a slice through this interval and just figure out what the area of that one slice is. So this is a rectangle. Area of a rectangle is going to be the length, or length times width, or you could say the height times the width. And in this particular case, it might be better to think of the height times the width. Now the width is just that dx term, or differential. I haven't really discussed in detail what that is, but right now you can just think of it as the width of this rectangle. That's our dx. And that's important. That's telling me whatever expression I have here, I have to put it in terms of x. It has to be some function of x. Now the height is going to be this distance here, right? So that's going to be our top function minus the bottom function. So the top function was e to the x. And the bottom function is going to be this one, x squared minus 1. Now, I'm not sure if they're looking for you to put in or distribute that negative or not. You can. But in my mind, that's the area of that one rectangle, that one slice that you're taking through that region. In fact, let's go a little bit further. Let's actually find the area between these two curves for our interval -1 to 1. So that would be the integral from -1 to 1 of e to the x minus x squared plus 1 dx. Now I need some antiderivatives here, right? Antiderivative for e to the x is just e to the x minus what?
X cubed over 3 plus x.
Perfect. And that's between -1 and 1. Now it is a symmetric interval. This isn't an odd or even function so that we can't take advantage of any properties here. We're just going to get, excuse me, e to the first power minus 1/3 plus 1 minus e to the negative first power minus -1/3 minus 1. And let's clean that up a little bit. E to the first power plus 2/3 minus e to the negative first power to be plus 1/3 to be minus 2/3. Let's just double check here. And when we combine like terms, well, the only like terms that I can combine are these right here, right? A positive 2/3 and a positive 2/3. So that's going to be 4/3. I'll end up with e plus, no, not plus.
The negative, one step above, you have +1 minus a -1. Shouldn't there be a +2 down on the bottom somewhere? You have e to the 1 minus 1/3 plus 1 minus e to the -1 minus a -1/3 minus 1. If the negative carries through, we should have e to the first minus e to the -1 minus 1/3 minus 1/3 plus 2.
Well, the plus, I mean, these two together give me a +2, and then I'll have a minus 2/3. So
Right.
2 minus 2/3 would be 4/3. It'd be 6/3 minus 2/3. So
Did I jump the gun before you were done writing?
maybe that's okay. There. So I think we're good there. Now, as an added bonus, let's see if I can do this. Can you see the calculator here?
Yeah.
Yes.
Yeah.
Let's compare things. So, did I show this in my video or not? That you guys can do this numerical integration?
I
Yes.
think I saw this in one of them.
Okay. All right. So 9 is function integrate. So we want to go from -1 to 1 of e to the x. So second e to the x minus x squared plus 1. Oops, I don't need that there. And then you got to tell it what variable you're integrating with respect to. So that'd be dx. Now let's compare that to this numerically. So I want to compare e plus 4/3 minus e to the negative first power. Booyah! Nailed it. Cool. Cool. So, I mean, you're not ever going to be able to figure out the right answer or, this expression from these numbers, but you can go back and check it. And I encourage you to do that.
Yeah, if I was that good at guessing, I would live in Vegas.
Yeah, no kidding. Well said. Wow, that was a good one. All right, I'm glad we finished that one up. Any other thoughts on this or any other questions? This has been it's probably been our best Zoom meeting to date, I'd say.
I had a question, and I talked to Alonzo about this earlier on the phone. We had two sections, one that was left endpoints, right endpoints, and midpoints. And then the other section was Riemann sums. And I couldn't figure out what was the difference between the two as to why they'd have their own section. And then, so I just basically used the endpoint theories to solve the Riemann sum problems, and I got the same answer. Is there a difference between those two? Was there something?
You know, I've always been a little bit uneasy about those two sections together. And I think the big takeaway from that section is that, you know, you're finding the area underneath the curve and above the x-axis, or between the curve and the x-axis.
Right.
And there's a lot of different ways you can approximate that with left-hand endpoints, right-hand endpoints, midpoints, Gaussian points. I mean, not that that was covered in your book, but I mean, there's a lot of different ways you can.
Same as the trapezoidal thing.
Trapezoidal rule, Simpson's rule. There's a lot of different ways. But basically, I appreciate the question here. What happens is that this is just an approximation for a little bit of the area. And I got to do that for all of these. And what that gives me is a Riemann sum. Now, exactly how you find the height here doesn't matter, because eventually you're going to be taking and making these things really, really small. You're going to take the limit as, and you'll see it in a lot of the notation here, limit as the norm of the partition goes to 0. Basically, it's letting the width of these rectangles get really, really small.
Right.
And when that happens, that limit is going to become the exact area. Fortunately for us, that limit of the Riemann sum becomes a definite integral. And that's where the rest of our theorems in calculus really, really help us out, because now to evaluate that, all we have to do is find an antiderivative of that function. So that's what's wonderful about the fundamental theorems, is it gives us a much more powerful tool in finding these antiderivatives
Because integrating between the bounds, I find, is a lot easier than figuring out all of the rectangles.
Oh, I'm not going to place a lot of emphasis on the rectangles. I do want you to understand the rectangles, because the rectangles are a good way to approach finding these areas between two curves like we did here. And also in sections that are coming up, it's a good way to start finding volumes, because soon enough, you're going to start taking these things, rotating
the axis. I love spinning it around the
damn. Yeah, this is going to be your volumes of solids of revolution. If you look at a lot of components of modern day life, you will see that they look like they were turned around an axis. My water bottle, okay? Looks like
axis on that seam.
What's that?
If you roll it back a bit, you'll see the seam on the water bottle. There's your x-axis.
Yeah. So I mean, it looks like it could have been turned on a lathe, though, right?
Yeah.
So this could be thought of as a solid of revolution. And when I do these, I like to give you guys a really good geometric interpretation of these things, and you get that by slicing your areas, with a little rectangle like we did here. I don't know if you guys are interested or if you have more questions, but one of the things that I would enjoy doing is showing you how you come up with the formula for the volume of a sphere. You can do that now that you have calculus, now that you're starting to learn some more about the applications and integrals. So if you got some more questions, I'll do that. If you're not interested, I won't.
And volumes, the volumes, when we spin it around an axis, is that on the exam next week?
Yes. Yeah, that's
Then feel
section
free
6.2.
Jump right on in.
Yeah. All right. So let me get some more paper here. And let's see. Let's draw ourselves a nice little semicircle. All right, that's good enough. So this is a prelude to what's coming up. If you haven't already done the video for section 7.3 or 6.2, I should say. Sorry, I've been reading the book. Now, Matt, your question earlier, this is coming back at us. If you had x squared plus y squared equals r squared, that's going to be a circle.
Right.
All right, and if you solve for y, you get y squared equals r squared minus x squared. Y equals plus or minus the square root of r squared minus x squared. So, okay.
This has come up before when I was trying to take Calc 2.
Mm-hmm.
Almost always disregarded the negative because they were saying something about it's impossible to have a negative volume. Are we going to have the same situation here?
Well, we're going to disregard the negative because we're going to look at the axis. We're going to look at this function above the x-axis.
Okay. Okay.
So that's why we'll disregard the negative here, because we're just saying, you know what, let's just look at the positive x-axis, or the positive part of this, the part that lies above. It actually won't matter. You know, our goal, I mean, how do we get a sphere? If we take this and rotate it around the x-axis, then can you use your mind's eye to see what's going to happen? What's going to happen?
We end up getting
Yeah, you're going to get a sphere. Now, sometimes, depending on the particular problem, it becomes really tough to envision what these things look like when you rotate them around an axis. And here's the thing. You don't have to. You don't have to envision what they look like when they rotate them around the x-axis. Instead, what I'm going to ask you to do is envision what this is going to look like if you rotate it around the x-axis. My little dx slice. What's that going to look like when you rotate it around the x-axis?
It'll look like a disc.
It's going to look like a disc. All right. Now, here's my little disc. I tend to think of it as a hockey puck, but that's just me. And what I want to do is I want to find the volume of that one disk. And then what I'll do is I'll add up the volume of all such disks. So volume of one disk. Now, if you have questions as I go through this, chime up. All right, let me know. So let's see, the volume of one disk, well, I can kind of think of that as a very short cylinder. And the volume of a cylinder is going to be the area times the height. So where do you think it's going to get its height? What's going to be its height?
dx.
There you go, dx. So area times dx. As far as the area is concerned, can you see what this figure is? It's a disk. So the area is really going to be the area of a circle, which is going to be pi r squared. All right, so pi r squared times dx. So the question is, what's the radius? And that's going to be this little piece right here. That's going to be your radius. So what's that? What's that height?
That's the function that makes up the circle minus 0, basically, because we're just Off the dx.
Exactly. So the radius is going to be the square root of r squared minus x squared. Okay. And something nice happens here. I get the radius squared, and that squared is going to knock off that square root there, right? So the formula for the volume of one disk is just going to be pi times r squared minus x squared dx. Wow, that's cool. That's nice and simple. So but that's just a volume of one disk. I need to add up the volume of all such disks. Because this is a circle of radius r, that's going to be an r, that's going to be negative r. So, okay, fine, looking good there. We can integrate from negative r to r of pi times r squared minus x squared dx. Are we okay? So far, so good. All right. Guys, they're still all with me. I'm impressed. I took a peek at how many people are still in the meeting, and you're all still here. Good on you guys. Good on you guys. Well, the pi can come out in front. And you know what? I should probably do something here. Well, yeah. Let's take advantage of something here. R squared minus x squared over the symmetric interval. That's an even function. You know what? I don't want to make it too complicated on you. We'll just suck it up. So I took the pi out in front, negative r squared, or negative r to r squared minus x squared dx. Now the tricky part here is finding the antiderivative. And that's where it's so important. I get so annoyed when people leave off the dx. You're integrating with respect to x. So here, what's the antiderivative of x squared?
X cubed.
Good. So it's going to be x cubed over 3. But here's the tricky part. We're integrating this with respect to x. So it's as if I have r squared times x to the 0. The r squared is just a constant. When you integrate the x to the 0 power, you're just going to get x. So it's going to be r squared times x minus x cubed. That's the tricky part. And that's just another reminder that you always want to keep that variable of integration there. So I'll pause here for a second.
Hey, Jeff.
Yes.
How did you get the x again for the next to the r squared? Did you distribute the integral? I mean, I thought.
What I'm going to do is I'm going to think of the r squared as r squared times x to the 0 power, right? Because x to the 0 power is 1. So 1 times r squared is still r squared, right?
Yeah.
Now, because I'm integrating with respect to x, r squared is just a constant. I could have easily just written pi because r squared is a constant. The only variable is x. So if I'm integrating with respect to x, remember what you do when you integrate a polynomial term like that. You add 1 to the exponent and divide by that same exponent. So it leaves me with my constant, which is r squared, times x to the first power divided by 1, or basically just r squared times x. Does that help out?
Yes.
Okay, good. So let's fill in some values here. I get pi, and if I put in an r here, what am I going to have here?
R cubed.
Yeah, I'm going to have r cubed. So it's going to be r cubed minus r cubed over 3. And that's my upper limit. Let's keep this pi out in front for everybody. And at my lower limit, I'll have negative r times r squared, so I'll have negative r cubed. And then a negative r cubed again is going to be negative r cubed over 3. So, okay, let's see if we can't clean this all up. It's going to be pi times r cubed minus r cubed over 3 plus r cubed plus, let's see, it's going to be minus r cubed over 3. There's a lot of r cubes here. It's getting a little bit messy. So how about if I factor out the r cubed from everything? Pi times r cubed times 1 minus 1/3 plus 1 minus 1/3 again. Any guesses as to what that equals?
4/3.
4/3. In other words, 4/3 pi r cubed. Wow. That is too cool. That's cooler than my hat. Now keep in mind this. Archimedes is Samos. He's at the top of mathematical achievement along with Newton, Gauss, and Archimedes. The thing is, Archimedes lived like 2,000 years ago. He figured out this formula by using calculus when calculus wasn't even invented. So how smart is that?
Or electricity, or plumbing,
Or the internet,
or the internet.
or getting your pizza delivered. I mean, yeah, he did it in really rough conditions. So amazing, amazing, cool. All right, wow, quite a good session. Anyone else?
I have a
Does
quick
this mean
question.
that whatever volume, circle volume we get, just figure out whatever the radius is in 4/3 and we just bang that out? We don't have to actually do any work?
Well, yeah, if you were just given the task of finding the volume of a solid rotation when you're rotating a semicircle, then yeah, then the problem's already been done. All right, we got the volume of a sphere. But what's going to happen is that this function is going to be changing. So it's the process that you should get. Now, you're going to see two different things as you work through your work in section 6.2. You're going to see some figures where this is flush with your axis of rotation. That is, there's no, there's no gap between the axis of rotation and the figure. But for instance, what I could do, and if I wanted to, is instead of rotating it around the x-axis, what if I rotated it around a line like, say, down here, around y equals -2, for instance? Then I'm going to get a much different figure, and then you're going to have to do some work. And maybe there's a gap between these, so that when you rotate it around, instead of getting a nice cylinder, you're going to get a hole in your cylinder. And so that's going to mean the difference between a disk method and a washer method. So the disk method is what we just did here. The washer method is what we did, or what you would have to do if you're rotating around a line like y equals -2. So it'd be a much different figure and a much different calculation.
The memory serves, it's kind of sort of the same thing, but you're doing one for the big circle, one for the small circle, that's the cutout, and then you minus the 2?
Yep,
Okay.
exactly right. Cool. All right, great session here.
I have a quick question.
Yeah, please.
So would there be another praxis exam?
I'll try. This seemed to be immensely popular last time. Yeah, I'll try. And, let me give you a heads up that your scrap paper that you scan in is going to be more important this time than it was last time. So
Yeah, I know.
please take careful notes.
I'll make sure my handwriting is legible throughout the entire process.
Thank you. Thank
Was
you.
my, if you remember, was my handwriting fine?
I don't remember having problems with it, so I'll say yes. Yeah.
Okay.
Let's see, Lauren, any questions there?
No, I'm good.
All right.
I got a question. So I know you record the Zoom meet. By any chance, do you post them anywhere? Because I tried looking on
Yeah.
D2L.
Yeah, they're in the first tab in D2L. If you go to the content section, it should be Zooms and FAQs. So you'll find them there. This one I'll probably post on YouTube just because it was actually a really good one. And I don't know if it's okay with everyone here. Is there anyone that would prefer not be on YouTube?
No, I'm absolutely fine with it.
Anyone? Last chance.
Yeah, that's fine.
Okay. Hey, I got some questions for you. So let's see if I can't do a poll here. All right. So there's 8 of you out there, and just give me some feedback. So you should be seeing some kind of a button and able to fill in a poll.
How many
All right.
do you have on your YouTube channel now that we're all stuck at home?
What's that?
How many subscriptions do you have to your YouTube channel now that we're all stuck at home?
I think last time I looked, I was over 300. But here's the funny thing. I'm actually getting emails from people who aren't even my students like, can you send me the handout that goes along with this video? So that's kind of funny. All right.
Just throw some cool graphics in there and we'll see if we can get you monetized.
All right. All right. Thank you for all that. Let's see. I'll share the results. Everyone gave me a good thumbs up. I appreciate that. Let's see. There should be some other questions I had for my participants. So let me go back to the polling. So I'm trying to learn more about this stuff.
So, Jeff, I think that the camera addition today was very good.
Hey, thank you. Thank you.
I don't know if that's one of your questions, but I just wanted to say that.
Well, thank you. I've been waiting for it for a while. Let's see. All right. I appreciate you guys voting again. I had actually a couple more polling questions, and I'm not sure where they're at. This should have come up twice, or it should have come up with some different questions. So I'm not sure what's going wrong with that. And polling. Let's see. Oh, here we go. Yeah, here's the other one. Okay. Do you guys?
I don't see a poll. Oh, there we go.
There we go. So I'm curious to know how your learning experience is going online. There should be 2 polls here. Okay.
The online thing I think's fine, but I always prefer being in a classroom environment when I'm doing this stuff.
All right. Well, I appreciate the feedback. Just so you know, I made the feedback anonymous, so I'm not going to be looking going, well, who said this sucks? I appreciate the honest feedback. You know, it's helpful, and I'm going to continue to get better. And I hope that that's the way with all your instructors too. So,
Are they talking about putting all of OCC's classes online or something?
I believe that for at least the first semester part of summer, that I think they're going to be online, you know, May through June. I don't think that that's going to change. So,
Okay.
Cool. Well, and polling, share results. So I'm not sure if you can see the results, but there they are. So thank you for your honest opinions there. Was there anything else to wrap things up? No?
Hey Jeff, did you get my email as far as my test notes?
All right, we can talk about that afterwards.
Okay.
So let me pause the recording here. Let's see. Naseem, how you doing today?
I'm okay. I just had a quick question about the 6.1 videos. There's quite a lot of videos on YouTube. And I was wondering, is there a specific one you want us to watch? Because I watched the 2019 one.
Yeah, that's probably the one that I would recommend. If you're just going to watch one of them, you know, it's something that I had Terry working on, and I've fallen off of that, you know, having him give me his perspective on, do you need to watch all of them? You know, it's just one of a long list of things on my to-do list. And if you're just going to watch one, I'd watch the most recent one, which would be 2019.
Sure, like how much do they differ from each other? That's all. Like I just didn't be lost.
Yeah, man, it's been 4 years since I created the other two, so I don't know.
Okay, I got you.
I think if you watch the 2019 one, it's probably pretty good. And you know, if you have problems in the homework, then maybe you can try the other videos. You know, see if you can pick up something new. But I think today's session we did a little bit on area, so that might help as well.
So
Yeah.
The problem comes in 2016, it was a prior edition of the book, and so the numbering and the homework assignments don't match.
Yeah, that's why it was a little confusing. That's why I prefer to watch the latest one, but I just wanted to make sure.
Yeah, that's what's going on.
Thanks for the reminder on that one, Terry. Yeah, they are a little out of sync in that respect.
Okay, thank you guys.
Yeah. So, anything else?
All set.
All right. Well, thanks so much for hanging out for quite the extended version of our class, and I hope that was helpful. And Louis, I don't know if you're still there or not, but
Yeah, I'm still.
okay. Yeah, I'll see about posting this one on D2L. Well, I mean not D2L YouTube, but I'm not sure what to title it or where I put it in terms of sections, because we mostly did section 5.5 stuff, but we also dabbled in 6.1 and 6.2. So I don't know, I'll think about it. But
I was able to find the other one, so I'm definitely going to go back and you know, I had one last question too. So I know we're having the exam next week. We're still having the final as well, like not the week after, the week after that, correct?
Yeah.
Oh
yeah.
no, wait. I don't have the dates. I forgot what week it is, but I know.
We have an
it's like
exam
2
next week and then the week after that too, right?
Yeah.
Yep.
So yeah, the exam's the next 2 weeks. Next week is exam 4, and then after that is the final exam.
Okay.
Final exam, I'm thinking might be on the 30th, but I'd have to look at my calendar.
I think it was the 30th. I have to look at mine as well. But
Okay.
other than that, I think that was all my questions.
Great.
Would there be a praxis exam for the final?
I'll try. It's really daunting because
If we practice exams for the previous exams, would that basically cover the same thing?
Yeah, I mean, they do. I mean, because this class is is moved to online, and I don't have quite the freedom that I normally would have in writing a final exam. I'll try and make a final exam preview on WebAssign. Just be prepared that it's going to be freaking long. It's just going to be long. There's not much I can do. And, you know, but kind of like the last one, you don't have to do it. It's, you know, it's advisable. And the problems are probably going to come directly from that final exam review. They're going to be on your final exam. So, but you don't have to do it.
Okay.
All right. Well, thank you so much, everybody. I will try and post this, and we'll be around on Thursday as well. So make sure you work on section 6.2, get some questions answered on Thursday, because that's a challenging section. There's no doubt about it. You'll see it again in Calc 2, but you know, it's probably a good idea to master it now.
Okay, perfect.
All righty.
All right. Be safe, stay in, and we'll see you Thursday, same
Right.
time.
See you, Jeff.
All right. Alonzia,
Good day.
you want to hang out for just a second?
Yes.
I seem to remember looking at some of your work. I do think I credited you. I have to look back. I did credit you some for, you know, some of the little twists and things like that you said. But I've kept your email open because I wanted to look back at it and try and take a more concentrated look at it. It's just
Okay.
it's just on the long list of to-dos. I know that I think it was problem number 2 that I gave you some points there, but I'd have to look back. But like I said, I still have your email. It's open, and yeah, it's just on a long list of to-dos. I mean, I answered 60 emails yesterday for instance.
Okay.
So that, and I'm trying to learn this, you know, new toy here. It's just a lot. Plus, I'm going through some training myself with that Zoom stuff. It's wow. But it's still open on my desktop, and that's my way of not forgetting it.
Okay. Well, that's fine.
All right.
All right. Thanks a lot.
Take care.
All right.
Bye-bye.
All right.